Artimonorec is a monocular depth estimation network trained in a fully self-supervised manner from stereo. The project builds on Monorec, which was developed in collaboration between Artisense and TUM and was published at CVPR 2021. The main focus of the project has been to demonstrate that Monorec can be adapted to the Artisense sensor setup and deployed in a real-time scenario. The core idea of the approach is to use a visual tracking system to generate training data for a deep learning model. For this purpose, we use the in-house developed Artisense VINS, which fuses images from a stereo camera pair with inertial measurements from an IMU to calculate both the trajectory of the camera and a sparse 3D map. Using VINS, we are able to generate high-quality training data for Artimonorec without the need for a LiDAR or other depth sensors. This significantly reduces the effort required to deploy the system in previously unseen scenarios or sensor configurations. Instead of using images directly as network input, Monorec uses 3 consecutive images together with the poses from VINS to compute a photometric cost volume, which encodes the geometry of the scene. In order to handle dynamic environments, we also predict a moving object mask for every frame, which is used to filter the cost volume before it gets sent to the depth network. The training pipeline is composed of multiple steps. In the bootstrap stage, we train the mask and depth network separately using multi-view photometric consistency for the depth module and auto-generated ground truth masks for the mask module. And then in the refinement stage, we fine-tune the two networks together using stereo supervision and a loss function designed to balance the two components. For the bulk of the training, we use the Artisense dataset, which has been collected previously by Artisense and is available for public use. We also further train and test the network on a separate scenario where the camera is mounted behind the windshield of the car. Here we show the network output on a segment of one of the sequences. We have the camera image to the left, moving object mask in the middle, and the depth prediction to the right. The network is able to run in real time in parallel with VINS on a Jetson Xavier after switching from SSIM loss to L1 loss and reducing the number of cost volume planes from 32 to 16. And this video shows a 3D view of the reconstructed sequence after filtering out moving objects. And here we highlight some sections of the trajectory. And here are some example images comparing the auto-generated ground truth masks with the network predictions. In the bootstrapping stage, we use a pre-trained object detection network to get the locations of classes that tend to be moving, like cars and pedestrians. We then use a series of heuristics to roughly determine which of the detections are actually moving. This process is error-prone and, for example, misses a lot of cars, but it provides a good enough starting point for the refinement stage. As an illustration, the top row shows an example where the heuristics have failed to find any of the cars in the image, but the network still produces the correct prediction. Here we show the benefit of the moving object mask on 3D reconstruction. Before adding the mask, we can see significant artifacts around moving objects. For instance, cars often appear much closer or further away than they actually are, which would cause problems in autonomous driving scenarios. However, with the moving object mask, these artifacts can be filtered out effectively. In the future, Artimonorec can be used to enable various downstream tasks, such as path planning, object tracking, and large-scale 3D mapping, both in indoor and outdoor scenarios. Thank you for listening, and thanks to ELISE for funding the project.